is Fred Leve from the Air Force Office of Scientific Research. And as I mentioned this morning, I had a grant, when I got my PhD, I got a grant to go any place I wanted in the country, and it came from the Air Force Office of Scientific Research, so thank you.
Okay. On behalf of my colleagues, you're welcome. Thank you. All right, so this talk will be quite a bit different than the other talks. I'm an aerospace engineer, and I used to work on research for precision pointing and attitude control of spacecraft. So this will be, the application seen here will be spacecraft pointing. And the title, as you can see, is Singularities Are Not Created Equal. For inverse kinematics, a lot of people treat all singularities as the same, but some singularities I'll classify in type here as being passable, impassable, one's a different dimension, and all that information is very important for the design of the system, its and its arrangement, and as well as planning to get around the singularities. Okay, first, why are we here? I'd like to thank Professor Smale for his breakthroughs and research, and his students' research, and the students' research in dynamical systems, algebraic, and differential topology. A lot of those great works have motivated me to look into these fields over the years. I was not trained in these as an aerospace engineer, and I found it very powerful in describing things I wanted to formalize. And so happy 95th birthday, Dr. Smale. Okay, so the goal here is to have a spacecraft moving around Earth very fast to do precision pointing. So for inverse kinematics, basically you're given a trajectory. You have to stay, you could think of it, you have to stay in a fiber. Like every point you have to meet at every time. You don't have wiggle room. You can't perturb. And the reason why you don't want to perturb is because these actuators cost millions of dollars a piece. To their most precise actuators for agility on spacecraft. Reaction wheels are slow. They're also very precise, but they're for science spacecraft. You don't want to perturb the Hubble Space Telescope when it's integrating light from billions of light years away, right? Well, you don't want to perturb a spacecraft moving around really fast when you're trying to take images on Earth, right? So practically, you can't treat it as a geometric problem. It's actually an algebraic problem with the maps. Okay, so what is a kinematic map? The maps we're dealing with are kinematic maps. Typically, you see them from like Cartesian product S1s or an n-dimensional toroid, which would be joint angles into, R3, SO3, or SE3, right? This is typical classical problems. For the problem I'm looking at here, it's going to be R3. I'm assuming R3 because angular momentum, I'm assuming are vectors in R3 for the spacecraft, okay? There is really no difference mathematically between serial manipulators, revolute joints, and actuators, control moment gyroscopes, which are gimbaled wheels that rotate at constant speed that are gimbaled. These things rotate spacecraft by the conservation of angular momentum. And the reaction wheels, which are just accelerating rotors, are fixed. They have fixed axes, do the same, but they don't do it gyroscopically. They don't produce as much torque. So you don't want to use them on things that need to move around really fast. Okay? So from the map, the kinematic map, we get the kinematics. It's a differential equation, and this is the Jacobian associated with it. And I'll talk a lot about this in the sequel. So kinematic singularities are defined where this Jacobian is rank deficient. Singularities maps, in differential topology, this is all really well-known stuff. It's nothing new. Okay, so naively, you would think, okay, at each x, I do more Penrose inverse or something, right? I try to solve, y equals a of x times x dot for x dot. First of all, you would never use the matrix form here. It's a horrible idea. Second of all, you should use SVD, singular value decomposition. More Penrose would be where this z is 0. This would be null space solutions, or called null motion. And this would be the reduced this comes from the reduced singular value decomposition. This is essentially the more Penrose pseudo-inverse from the reduced singular value decomposition. And again, I took the singular value decomposition of A transpose, and the reason why is horizontal matrices, vertical matrices are easier to take singular value decomposition of. In the transpose operation, you have actually less operations by doing that and transposing it than you do in the horizontal matrix. Okay. One thing I should say right here is that if you have the number of actuators greater than or equal to 3, because again, this is an R3, is the codomain, and you have full rank Jacobian, you can use more Penrose universe and you get an exact answer, because you can essentially get y equals a of x dot. Okay, so at singularity, when you have 0 singular values, you have the answer, right? It's the reduced singularity composition. That's essentially the best you can get at singularity. And I haven't told you what different singularities are yet. I'm just saying, treating all singularities the same, you have that given to you, okay? But near singularity, where this becomes actually hard, you have to trade error for a large norm, okay? Because you're essentially putting, where there's 1 over zeros for the more Penrose pseudoinverse, you're making 1 over 0, 0, or 1 over a very small number 0. So you're essentially like truncating it, okay? So you're trading a significant error, like a norm 1 error, for a large, sorry, this is the error, for a large norm, okay? Well, actuators have constraints. You can't have an arbitrarily large norm for a practical system. So you can't do that. You can't implement this. You don't want to just perturb the system because you spent millions of dollars on actuators that are 1,000th of a degree accurate to do precision pointing and take images. So this is also a bad idea. So what do? You have to have something that has the minimum amount of error but also meets constraints of the norm. That's the goal, right? Okay. Well, that's what steering algorithms do. So that problem you had before had the general solution with the singularity composition more Penrose inverse and the projection onto the null space. That z vector is any vector you're projecting with that u2, the left singular values, the right singular values, sorry, A transpose, onto the null space. So what you want to do is you want to use that null space, if you can, to increase the rank of the Jacobian simultaneously so that you get the exact solution. You get an exact solution that doesn't perturb the system. That's the goal of steering. But you can only do that if you have nice singularities, ones that you can get out of by using the null space. Those are passable singularities, okay? And that's defined here. Also, you'd want to know how to maximize the amount of workspace. So you want to co-restrict, either arrange the system in the best way possible, but also co-restrict the codomain so that you steer around in the workspace in places that are bad, right? That's another goal. And what you don't want to do, but sometimes you have to do if you're trying to use the entire workspace, is you don't want to perturb the singular values to get a full rank Jacobian while at the expense of having imprecise control. Okay, so the questions you should be asking are how to arrange the system of actuators. Say I give you a fixed number of actuators, you arrange them in a spacecraft. How to arrange them to make it easier to avoid points in that workspace that contains singularities. That's the first thing. You want to do the design first, okay? Now, how do you formalize what are good and bad singularities? Well, you should know that before you actually do the design, I should say. And what do I define by easy singularities? How do I know that I have only easy singularities in that arrangement? So minimally redundant arrangements have 4 actuators because my codomain is 3 dimensions, right? So a minimally redundant system has 4 CMGs. These are 2 examples of minimally redundant systems. So most systems are set up to at least be this, okay? Well, I worked on my PhD on this one. This is horrible. This arrangement, by the way, this is the locus of critical values, I should say, and everything inside here, the higher dimension, the 3-dimensional, full dimensional piece inside here that fills it in, those are the regular values. These lower dimensional pieces that are stitched together, these are the critical values, and it's the same here. So this red boundary is all critical values, and all of this stuff woven throughout the workspace is critical values, and it's the same here. But this is horrible. And the reason why they came up with this arrangement is because this arrangement maximized the volume of the workspace in R3. So you had, you could think of it as like you think you have more control, but you sacrifice horrible singularities that are inside here that are woven throughout the entire space in the process of getting that control. It's a very bad idea. This arrangement has the same number of actuators, has less volume in R3, but has very simple internal singular surfaces. There's just 2 disks in the shell, right? But you still have these things in the middle. And the point of zeroing the momentum is actually a point of control that you want to have the largest angular momentum capacity in control. You want to keep going back to 0 when you're going from rest to rest. You don't want to bias because you lose control authority of the bias. So what they've done in the past when they didn't understand the singularities is they would essentially take 4 actuators, use 3 of the 4, in that box arrangement I showed you. And then you have this little ball, a 1H ball, 1/4 of the performance that's completely non-singular. You don't have a null space when you use 3 actuators and leave 1 as a spare and don't use it, right? So you can still get around 1H, like 1/4 of the performance and still use that, but this is horrible. You have 4 actuators for 1/4 of the performance. This doesn't make any sense. Why would you do this, right? So this is also impractical. But they've done this for many years, and they were the systems were oversized to account for the math, that they were worried about the math. That's essentially what the problem was. Okay, so how do you define passability of singularities? So they're defined this way, according to me. Anybody can argue with me. I could be completely false, whatever, but this is how I define them, so this is the way it is. All right, so you have singularities that are isolated points, zero-dimensional singularities. These are all coming from the fibers over any point, right, of a critical value. Any critical values, I showed you the locus of critical values. If I take the fiber over the map of those critical values, I get sets with these things in them, okay? You have isolated points. These are always singular, which basically means you can have no motion. There's no motion. There could be mirror images. They could have additional points, but you can't move away from them at all. Like you basically move at all, and you perturb the system because the only solutions are zero-dimensional points. You have sets of full dimension. These are singularities and maps. These are not singular locus in algebraic geometry. This is full dimensional pieces in the fiber with respect to the fiber dimension. Okay, these are degenerate. You can't use gradient algorithms on these either. You think you have no motion, you can move around, but everything's bad, right? These are locally passable. Basically, you can move around for a finite time and then get to good points, get to the regular points, and then bump out a singularity. But you're moving around the Earth really fast. You can't have 10 seconds when you're moving around the Earth in 90 minutes to get to a non-singular configuration to actually do control, right? So these are not as bad as these, but they're still bad. You still have to know you have them. And the ones you really would like to have internally are globally passable, which basically means at any point, because this is low dimensional, right? Positive codimension here in the fiber, you can jump off immediately, right? Doesn't matter where you are. Obviously, this is non-singular. You're already out of singular. You don't matter, right? Okay, so the fibers, like I said, give you the information, and we'll talk about that now. Okay, and this is the definitions, and again. Not only the topology of the fibers is critical, but how they're woven throughout the workspace, which is the geometry of the arrangement. You do not want all of the singularities woven throughout the entire space and separating the space because they're like a codimension, n-1, right? You don't want that to happen. Right? You don't want the separating the space because you have to go from one point of space to the other. Okay, so let's talk about that. Okay, here's an example. If I took two control moment gyroscopes and I had their gimbals parallel, this is an extremely toy example, but it's very easy to see. The torque vectors, these vectors here are these are torque vectors, and these are the spin axis vectors. Okay. When you take the Jacobian, when you get the Jacobian from this, I have these two vectors. These are the torque vectors, O1 and O2. Okay. You see O1, O2, S1, S2. The zero momentum configuration, these anti-parallel vectors, is singular. It's along a line. Because the torque vectors are along a line. So I have one direction for the Jacobian, right? So that's singular. The problem is there's only two solutions, and they're both singular for zero momentum, pointed inward or pointed outward. That's it. So basically what it means, that either one of those solutions you're at, you can move the gimbals around in a circle, and you have a circle of bad solutions. And it's full dimension in the fiber because it's one-dimensional. So it's bad. It's degenerate. You can't do anything about this. So obviously this is a poor design, but this is a very easy toy example to show that you can have problems like this. You can arrange the system that has all bad solutions that still has infinite numbers of solutions, but they're all bad. Okay, this is a more practical arrangement. This is actual arrangement people use. Okay, this arrangement here, this is bad. These are good. These are bad. So you actually have a locally passable singularity here. And the reason why here you have to move these a finite amount. This is the axis coming out through the top, this y-axis for both of them. You have to move this a finite amount to get to a point to get these before you can spread them out. And that could be, I think, like up to 90 degrees. I think it's 90 degrees. So that's really bad. So you have to know about that. And since you know you have this, you have to restrict the codomain. You can't use the whole workspace, but you can use most of it, let's say. So you still have to know the geometry of where they are. But you also define their passability based off the topology. And I'll explain that here. So, when you're defining good and bad sets, first of all, I should say, these are just pictures of the fibers. the locus of critical values is essentially defined by the zero set of this singularity measure, right? Because if you have any zero singular values, this is going to be 0, right? So this is the set of the set of critical points. Sorry, critical points, not critical values. The singular points, right, in the fiber are essentially this intersecting with the fiber, right? So the bad points of the fiber, and then the complement of that is the good points, right? That's left over. The real issue here is when you're trying to do cell complexes is you don't have a closed subspace, so you can't use every one of these. You have one thing that's like, open, one thing's closed, and two things that are closed, right? So you can't just use regular cellular homology. So you need a way of calculating a finite number of things, combinatorial structure. You can use the homology functor, you have to use like general homology. You can't necessarily use cellular homology here, but again, yeah. So you take single homology of the sets. You could treat this actually as a CW complex, ignoring the gamma p hats, the open sets, and you basically do this. So this is the results. I don't want to spend too much time on this, but this is something that's trivial, but I had to explain to people the difference between kinematic and coordinate singularities for 10 years. And I got really frustrated by it to explain that you can't do some transformation and make them disappear. They're always there. They're physical. They mean you don't have torque in that direction. The physics doesn't change because you did a transform, okay? That's pretty obvious conceptually, but it's just proven here. It's pretty trivial. For an overactuated system, the only because you still have redundant degrees of freedom. You could still have larger dimensional sets of solutions, but the isolated points are singular. You don't have singular good points. You don't have singular regular values, right? Sorry, regular points. Sorry, you don't have singular regular points. This is just existence of discrete singularities. This just proves discrete singularities by relative homology. You get relative homology by the long relative homology sequence. You in theory could compute these things. Here's some other results: impassibility, singular components, the number of singular component pieces, and existence of locally passible singularities. So basically, there's relative homologies you can calculate, and even the dimensions of these singularities to get that information. Here's the problem: uncountable number of fibers. So what's the point? Wrote this paper, thought somebody smarter than me would be able to figure this out. I have an infinite number of computations. What am I doing? Somebody smarter than me figured this out. So that's essentially the second part of the talk. Okay, so in kinematics, most of the time, you have sines and cosines, and you can lift the map, the kinematic map, in R2n, essentially, to an algebraic map. You can take sine squared plus cosine squared equals 1, and you have a whole bunch of those. Those help you restrict the domain and codomain. So you take this here, and this x is just all of these extra, you think of them, these real algebraic sets, right? And then you constrain the image here so that you constrain the codomain and the domain. So now you have this new codomain and domain. You have this new kinematic map. You have this new Jacobian. You have all this stuff, right? Well, because you've done this, you compute all of the same information because you've grouped the pieces of singularity, the pieces of solutions that are singular by dimension because of the Jacobian drops, okay? And you've also shown which ones are connected, from the stratification. I'll show you what I mean here. So this result by Martin-Helmer and Vidit-Nanda, he essentially did a variation of the Whitney-Tom and the Tom-Boardman stratifications they did. And they basically were able to show that for real algebraic varieties, I think they lift the complex, varieties, and then they project back down. Real algebraic varieties, you can get this stratification, you get the strata, you get the connectivity, you get all this information I talked about, and because of Tom's isotopy lemma, the fibers are stratifiable homeomorphic. So I just have to calculate the invariance for one point in each strata. One fiber, I should say, for each strata. That's it. You get the information, like very easily. There is some issues here. Connectivity is defined numerically. There's some problems there, but this is it. I mean, they figured out how to do this with finite computations because you're using the algebraic structure, and you get that algebraic structure because kinematic maps have a lot of structure. They turn into algebraic maps by just lifting them to a higher dimension. Okay, so Yeah, that's what I said here. They have software. They're adding to Macaulay 2 all the time. They present this stuff at the computational applied algebraic geometry workshops. Again, people smarter than me figured out how to do it in a finite number of computations. And I think this is really cool because not only does it tell you, the dimensions also tell you how many CMGs you need active, essentially, because how the dimension of the singularities you have, right? If you look around and you see you have a ton of redundancy and you say, I never have, regions of singularity that are three-dimension, in the fibers, because there's n actuators. I have the most I have is 2-dimension. Well, you can add enough redundancy there, then you can offset that. The one issue is you can never get rid of singularities, though. This is a proven, result. Kinematic singularities will always exist. There's not a global section. Can't get around it. There's ways of moving them all to the boundaries if you have 6 or more CMGs, but then you need 6 CMGs, right? What you'd like to do is you'd like to have something robust to failure, so if you keep losing a CMG, you still have the best possible control based off the original arrangement you chose, because you can't move the actuators once they're on the spacecraft. They're done, right? And these are the references, and this is the second edition of the book, hopefully with not as many errors as I had in the first edition, 2015, which I've been in severe depression over looking at my old appendices when I came back to the second edition. But it's the only book in the area. If you guys are interested, I'll send you the PDF. It's a lot better than the first edition. I'm telling you, I was moving from Albuquerque to DC and sleep. Yeah, it was bad. But yeah, this is the final edition, the second edition. I'm not writing it again, so that's it. That's my talk. And really quick, I'm just going to show you a video of my old simulator at the labs. If it works. Hold on, what's going on? There we go, hold on. So this is a 3,000 kilogram simulator. There was a cooler simulator at Honeywell. This has control mode gyroscopes and thrusters on it. This is precision pointing. It's 4 times sped up. By the way, fast in space is degrees per second. It's boring because you can't excite the spacecraft. You can ruin the spacecraft. But you see, this is holding up it's on an air bearing. It's pointing and holding. That's how balanced it is. A 3,000 kilogram test bed at an angle. All right, now I'm done. Okay. Thank you.
You want to go?
Go what?
To space.
No. Absolutely not.
Why not?
Because and they're kinematic ones. You can't get rid of them. No, it's scary. The spacecraft environment is a headache. When you build spacecraft and you're working on the guidance navigation control subsystem, you talk to the other subsystem people and you just make them very angry because everything you've done is creating more problems for them. You have this thing, you have more computation, you create more heat. Thermal people get out of my face, right? You don't have power because your hair dryer has more power than a spacecraft, right? The most powerful comm satellite in the military has you could see this online. It's 5 kilowatts. I think your GPU and your servers that you're doing fluid simulations on would be the size of the Greyhound bus-sized spacecraft's power system.
So I want to go because I'm naive.
Well, don't look up anything about it if you go. That's all I'm saying. Oh, I got to take this off. Sorry. Oh, there's a question. Oh, sorry.